Previous time we discussed with you that in statistics we use sample instead of the population, and in econometrics we follow absolutely the same approach to estimate some linear regression function. And we are going to start our discussion with the simple regression model, because this model can be used to study the relationship between some variables, and simple because it's used to find the relationship between only two variables, between only two factors. Of course, this model has limitations as a general tool for some empirical analysis, but sometimes this is an appropriate tool to empirical research. But our main goal, we need to learn from this simple regression model how to interpret the regression model in general. And this is really good practice for studying some multiple regression analysis, which we will do in subsequent lectures. So we will start with the simple regression model today. We discuss some assumptions next week. And after this, we turn to multiple regression analysis. But before our main discussion, let's discuss some simple example. Imagine that you want to examine how the price reduction can boost coffee sales. And our general hypothesis that if someone offers a cup of coffee for a low price, it means he boosts sales in general. And of course, it's very unlikely that you can go to, let's say, every place where you can buy a coffee and collect data, because it's really difficult to study the sales and prices every place selling coffee. Let's say that we are interested in the St. Petersburg market. So we have a restriction for ourselves. Let's say that we want to know only about the market in St. Petersburg. And instead of this, we can collect a sample data from a population, as usual, yeah? And we use the regression analysis after this to calculate the average sales at a certain level of price. Let's take a look at this scheme. So here you can see a population and some sample. We continue our discussion about the coffee. We can say that population here is entire group that you want to draw some conclusions about. So in our case, this is all places where coffee is sold. And when your population is large in size, as in our example, because only in St. Petersburg there are more than 5,000 places which sell coffee. Or, for example, your population geographically dispersed or sometimes difficult to contact. So instead of this, we need to use a sample data and sample some specific group that you will collect data from. Of course, the size of sample is always less than the total size of the population. And all statistical techniques can be divided into groups. Could you hear me? Because I have some message about the bad network quality.
Yeah, I hear you.
Okay, so if it will be some problem, let me know, okay? So all statistical...
Yeah, I'm sorry. I have some прерывание sometimes in your voice, but I think
in my sound.
Yeah, now we have problems.
You hear me well? Okay. So we can divide all statistical techniques in two groups, in two broad categories, in descriptive statistics and in inferential statistics. And what can we do with the descriptive statistics? We can use this technique to describe the characteristics of some data set, the features of the population, or the features of the samples. And in statistics, we used to this for rely on probability, and we use this at the drawing some conclusions from the model estimation. We focus on making some predictions or some generalization about a larger data set. So we can use this type of statistic to check some hypothesis testing, to regression analysis, to correlation, and so on. And if you remember our previous example from the previous lecture, about the training and about the wage level. We discussed previous time that as economists, we are interested in questions such as if one variable, let's say in our example, this is training, changes in some certain way, by how much will another variable, let's say level of the wage, change. And this equation is called a single equation model. We will talk today about this example. I mean, when we have only two factors, simple regression model. And of course, we also said that we have some other factors that can affect our dependent variable. And in this case, we will talk about the multiple equation model. But much of applied econometrics begins with some statement that y and x, let's say this is y and this is x, are two variables representing some population. And we are interested in studying how y varies with changes in x. So in this example, in the wage and training example, we want to explain why wage in terms of x, in terms of training. And when we use purely mathematical model, like in this case, in the functional form case here, of course, this equation is of limited interest to a econometrician, yes, because we discussed that it assumes an exit, or in other words, deterministic relationship between wage and training. So if we have, let's say that if we obtain some data on wages and training of some sample, let's say 500 workers, and then we plot this data on some graph with wages on the vertical axis and training on the horizontal axis, we will not expect that all these observations from our sample will lie exactly on the straight line, because it's very simple to assume that only training can affect the level of wage of some average person. Of course, this is not true, because there exist a lot of other factors that also can affect the level of wage. And because of this, plotting this scattergram, you can see exactly straight line with all the plots on this line. A relationship between economic variables, between business variables, of course, are generally inexact. And how can we express this? So if we want to allow some inexact relationship between factors, between economic variables, we need to modify our previous equation and our deterministic function as follows. So here we can add one more thing, and this is U. In general, we can call this disturbance or error term. This is some random stochastic variable that has well-defined probabilistic properties. And this term may well represent all those factors that affect wage, as we continue our previous example, affect wage, but are not taken into account explicitly for some reasons. More technically, we can call this equation as an example of linear regression model. And this is our major concern for this lecture and for the next lecture. So if you remember, during the previous seminar, you have an example about the teaching assistants and student performance. And one of the questions in that example was about the error term. So I hope that now you understand what does it mean, and it's clear why do we need to add these disturbance in our model. And also you should remember some definitions. You should remember that Y is called the dependent variable or explained variable or response variable, predicted variable, the regressant or left-hand side variable. So there are a lot of definitions. And also X variable, we usually call as the independent variable or explanatory variable, or sometimes we can say predictor or regressor, covariate, right-hand side variable, but usually we will use dependent, independent, or explained and explanatory in most situations. And also you should remember that independent in this definition that concern our X doesn't mean something about the statistical notation of independent between random variables. It's just a definition. So it means that we want to explain our dependent variable Y in terms of X. So, and also, of course, this is our error term, or let's say that this is our disturbance that represents some factors, some other factor that can affect Y, not only X. Okay. And also we need to start our discussion about the simple regression analysis or linear regression analysis with the concept of population regression function and with the concept of sample regression function. What is the difference and what does it mean? First of all, you need to understand that expected value is a key concept in regression analysis. And all the regression operates with conditional mean. So each conditional mean is some function of x where we can write this as following. So function of x denotes some function of the explanatory variable. And this equation we call as the conditional expectation function or population regression function or just population regression. So it states that the expected value of the distribution of our y for some given axis is functionally related to x. And in other words, we can say that the mean or the average value of our dependent variable varies with different level of x. And to find the population regression function, of course, first of all, you need to determine dependent variable and independent variables. And also you should understand how can we measure them, as well as we need to understand the mathematical function, the relationship that can describe how the variables are related to each other. So if we talk about the regression function, before we construct our model, we need to take into account the form that the function of x assume. What does it mean? So sometimes we can talk about the linear function, sometimes we can talk about the quadratic function, and so on. For the simplicity, we can start our example with the linear function of x. For example, in general, economists might posit that consumption expenditure is linearly related to the income. Our first approximation of our hypothesis, we may assume that the population regression function is just a linear function of x. So y and x linearly dependent. And the basic idea of population regression function, that the population mean value of the dependent variable on the basis of the known values of the explanatory variables from our sample. So we can express this mathematically in the following way, in the following form, at the straight line here. So we have two parameters, beta 0 and beta 1. And these parameters are unknown, but they are fixed. Also, we call them regression coefficients. And beta 0 we call as intercept. And beta 1, this is our slope coefficient. And this equation itself is known as the linear population regression function, or sometimes we call this linear population regression model, or simply linear population regression. And it's very important to understand that conditional analysis on x here doesn't mean that x causes y. What does it mean instead of causation relationship? It just only means that we want to see the behavior of our dependent variable, of our y, in relation to our x variable, or to our x variables if we will talk about the multiple regression model. So it's very important to understand that all our ideas about the causation must come not from outside statistic. These ideas about the causation should come from theory, or we can use some advanced econometrics techniques to find the causation. So we must appeal to a priori or theoretical considerations. Now let's discuss some simple example to understand the idea of population regression function. So this example comes from the genetics. And we collected and studied high data from families, and we want to understand the heredity. So we have some data on the son's height and the father's height. A question is, how well can we predict a child's height based on the parent's height? So our concern is predicting some mean value of height of sons, knowing the height of the fathers. This is a scattergram, and suppose that we ask to guess the height of a randomly selected son, but we don't know his father's height. So the answer on this question, the best answer on this question, will be some average distribution computed on this subset that will be our best prediction in this case. So for any given value of x, the distribution of y is centered about the expected value, as illustrated in this figure. So this is not surprisingly that the centers of these groups are increasing with high. And these centers appear to follow a linear relationship. You can see this relationship here. And if we connect the circles, these connected circles are formally called like a conditional mean or conditional expected values. So this is probability regression line, and this is population regression line tell us how the mean value of y or any other dependent variable is related to each value of x, or in other terms, to our independent variable in the whole population. So the population regression line passes through the conditional means of y. And technically, the dependence of y on x can be defined simply as the mean of the distribution of y values, which has some given x's. And if we want to write this concept of population regression function, we can use this equation. So we can say that the deviation or our error term, some unobservable random variable that taken positive or negative values, and of course in statistical and in econometrical relationship among variables deal with a random or stochastic variables that have some probability distribution. And this relationship holds on average, but of course this relationship can have some errors. And because of this, we need to add these errors with some specific observation. So we need to specify, let's say, the random nature of our model. And the error term here represents this difference between these observed points and between our estimated dependent variable. So here you can see the conditional mean of the dependent variable derived from your model. So we can express the deviation of the individual dependent variable around some expected values. And for this, we use following equation. So it's very important to understand that we can express our regression function using two things. The first thing we can express are the systematic or deterministic component. And this component includes beta 0 and beta 1 parameters. We need to find them. This will be our goal. But also, the second component, some random and non-systematic. And of course, we will discuss next lectures why can we have this systematic, unsystematic part, this random component. But there are a lot of different reasons why we can't include all the emitted variables into the model. There are a lot of reasons. For example, some incorrectly measured data, or let's say unavailability of some data, because of course we may not have some quantitative information about the variables. It's impossible to us collect all the factors that can influence our dependent variable. Sometimes the reasons that we can't include some factors because we have a lack of theoretical insights to fully account for all the factors. And because of this, maybe our model could be incorrect in these terms. Or maybe our functional form could be incorrect. For example, we say that the relationship is linear, but instead of this, the relationship is not linear between dependent and independent variable. And also, every time we can have some unobservable characteristics, some unpredictable elements that, of course, can influence our dependent variable. Let's say that this is intrinsic randomness in form characteristics or in human behavior, or some intrinsic randomness in individuals or in households that cannot be explained no matter how hard we try. That was about the population regression function, about the population regression concept. But we start our discussion today that instead of population, we work with a sample. And our main purpose to find beta 0 and to find beta 1. So how can we do this if we have the whole population? If we have the whole population, it's very, let's say, straightforward task, because we just need to find the conditional mean of y corresponding to each x, and then we can join these means and find the answer, what is beta 0 and what is beta 1. But when we work with a sample, this task is not so easy. let's take a look at this example. We have two samples. In this table, you can see the data from the one sample, and in this table, you can see the data from the second sample. But both of the samples come from the same population, absolutely the same population. What can we do? We can plot the data of both tables on one graph. So we obtain this scattergram shown in this figure, and here you can see circles, and here you can see some crosses. That means that circles come from one sample and crosses come from another sample from the same population. So through these scatter points, we have drawn visually two straight lines that, let's say, that fit the scatter points reasonably well. And both of these lines we call the sample regression lines. So let's say that sample regression line 1, sample regression line 2. One of them based on the first sample and the second one based on the second sample, respectively. So the question is, which of the two regression lines represent our true population regression line? What do you think?
I think it's somehow average between of them or some stuff like that.
So we need to draw one more average line here. Yeah?
Probably.
Probably. Okay. The answer that there is real and we cannot be sure which one is better represent our true population regression line. Because in general, there is no way that we can use and we can be absolutely sure that either of the regression lines in this figure represent the true population regression line, or maybe not line, curve. So if we have, for example, one more sample, another sample, and we draw one more line here, so you imagine that you can see here sample regression line number 3. Again, it doesn't matter. It doesn't mean that sample regression line 1, 2, or 3, some of them will be the best one. Because, again, we don't have any way, no way that we can be absolutely sure which of them. And the concept of sample regression function can be written in the same way as the concept of the population regression function. Again, we can write y as the dependent variable, x as the independent variable, and again we need to find two parameters, two unknown parameters, beta 0 and beta 1. The difference is that in our notation we use hat above each parameter and above our dependent variable. So we read this as u hat or cap. And what does it mean? This hat means that y is an estimator of the population conditional mean. This is an estimator. And also beta 0 hat and beta 1 hat are estimators of beta 0 and beta 1. So this is sample statistic. The different, you need to understand the difference between two definitions, estimator and estimate. So estimator means only some simple rule or some formula or some, let's say, method that tell us how to estimate population parameter from the sample. And when we obtain some particular numerical value using by this estimator, we call this an estimate. So this is the difference between two definitions. Please use the definitions correctly, properly. And again, as we just discussed the concept of population regression function, that of course we need to add some stochastic part. Also, we need to do in the sample regression function. So sample regression function can be expressed also in this stochastic form. And what is the difference? Again, we add here the error term, but with the head. And in this case, we call this a residual term. And the reasons why we should include this residual term is absolutely the same as we've just discussed in the population regression function. So let's sum up the main idea. The main idea of this concept that we find our objective in regression analysis is to estimate population regression function. But as we don't have all the data, all the population data, instead of this, we use sample regression function. And we have a randomly selected sample of y values for some fixed values and levels of x. And we can estimate the population regression function, but not accurately because of some fluctuations, because of some sample fluctuations. And because of this, our estimate of the population regression function, population regression line, based on the sample. And this is our best approximation, a best one. Now, let's talk about one of the main methods, one of the popular methods that used in the regression analysis. This is ordinal least squares method. Maybe you heard something about this method. And I should say that under some assumptions, we will discuss some of the assumptions today and some of the assumptions next week. So under these assumptions, the method of least squares has really very attractive properties, very attractive statistical properties. And because of this, this is one of the most popular methods of the regression analysis. And this method is rather simple. So let's take a look. We continue to work with the simple regression line, with the simple regression model. So today we discuss only the model where we have only one independent variable. So our main idea that we use sample regression function and use this equation. So we are y hat here is the estimated or the conditional mean value of our population y. And here the residuals, this term, is simply the difference between the actual and estimated values. You can derive this from this equation, you can see this. So it's better to discuss the ordinal least squares method through this picture. So here you can see that we have some n pairs of observations on y and x. We have two random variables. And our main goal, we want to determine, we want to find the sample regression function, or we want to derive the sample regression line. Why? Because we need to find these two parameters, these two unknown parameters. But we have an idea how to draw this line. Of course, we want to determine this line in such a manner that this line will be as close as possible to the actual observations, to these points. And in other words, we want to draw this line in such a way that the sum of the residuals, this is our residual, this is our residual, this one and this one. So the sum of this distance will be as small as possible. And this is our idea, and this is the idea behind the ordinal least squares method. But if we take only just the difference at the residuals between the observed and between the estimated y values, what does it mean? It means that we give equal importance no matter how close or how widely scattered the individual observations from the sample regression line. So in our example, if you compare this residual with this one, you can see that the distance, of course, is different. And it not will be good if all of the residuals receive equal importance, no matter how close the individual observations are far from our line. Because here, this one and this one are scattered more widely from our line if we compare with these two residuals, yes? So in some cases, of course, our model, our sample regression function can underestimate, or in some cases can overestimate the true population regression function. So the critical question here that we need to answer, can we devise some rule that will make this approximation as close as possible? So we need some rule. And the second question, how should the sample regression function be constructed so that our estimate beta 1 and beta 2 will be as close as possible to the true parameters? So we need to find best fitting sample regression function. And of course, we need to do this even we never know, we never actually determine the population regression function, because we will never know the true beta 1 and beta 2. True parameters, we will never know. So what is the idea? The idea behind this method is really very elegant and simple. But we need to hold some assumptions. As every method, as every approach, if this approach that we need to find, we want to work correctly, we need to hold some assumptions. Most of them we will discuss next time, but two of them we will discuss right now because these two assumptions are very critical for this method. So the first assumption, that the average value of y, of our error term in the population is 0. And what does it mean? This assumption says that the positive values of our error term cancel out with the negative values, so that the average value of our u, of our error term in the population is 0. And also we include the intercept in our equation, and as long as this intercept included in this equation, nothing is lost by assuming that the average value of our error term in the population is 0, because every time we can redefine the intercept. And this is not a restrictive assumption, because we can always use our intercept to normalize this assumption. And we have one more assumption. And this assumption is crucial. This is really a critical assumption about how our error term and x are related. So this assumption means that average value of our error term doesn't depend on the value of x. So the average value of some, this is our unobservables terms. So the average value of the unobservables is the same across all slices of the population determined by the value of x. And when this assumption holds, we say that the mean value of our error term is independent of x. And of course here mean independence means full independence between our error term and between our independent variables. Let's continue our oral example about the wage and the training and about the education. What does it mean, this example, in the context of this assumption, in the context of our example about the wage? So this assumption requires that let's say that our dependent variable, again, wage, our independent explained variable is education level, and in the error term we talk about some innate ability. So it's really very hard to include and to measure innate ability in our model. So let's say that these innate abilities will be in the error term. So this assumption means that the average level of innate abilities will be the same regardless of years of education. So if the average ability for the group of all people with 8 years of education must be absolutely the same as the average ability among people with the 16 years of education or more than 16 years of education. So it doesn't matter. This assumption means that the average ability level must be the same for all educational levels. And if, for example, we think that the average ability increases with years of education, or we can assume this, yes. For example, when people with more innate ability choose to become more educated. in this case, we cannot hold this assumption. And this will be a problem for the ordinal least squares method. So does it make sense? What does it mean? Okay, I hope that it's clear. And in other words, the same assumption about the unrelatedness of our error term and about our independent variables, we can rewrite in the manner of covariance. What does it mean? When we want to derive the ordinal least squares estimates, we need to realize that one of our main assumptions that we've just discussed also means that our error term is uncorrelated with our x. So in other words, we can say that the expected value and the covariance between x and between our error term is 0. So there is no any correlation or covariance between our error term and between our independent variables. This follows from the basic probability. What is covariance? I hope that you remember what is covariance mean. So covariance is linear dependence between two random variables. And it's defined as the expected value of this product. So also, if we use this approach, we can write our restrictions that we've just discussed, assumption 1 and assumption 2, in this case. Or we can rewrite this as following. So these equations just a second. Yes, we can rewrite this using two restrictions. And here we can see that we can use beta 0, beta 1, our unknown parameters, and say that this equation equals 0. So here we imply two restrictions on the joint probability distribution in the population. So since there are two unknown parameters to estimate, these equations can be used to obtain our estimators of beta 0 and beta 1. So if we can solve these equations, we can find them, beta 0 and beta 1, I mean. And this is called method of moments. This one and this one called method of moments. And the method of moments, this is some general approach to estimate that we use to implies imposing the population moment restrictions on the sample moments. So what does it mean? Let's say that for expected value of x, the mean of the population distribution and sample estimator is simply some arithmetic mean of the sample. And we want to choose values of the parameters that will ensure that the sample versions of our moment restrictions are true. So the sample version will be the same, but we correct by the number of observations. So you can compare that we use the same equation, but instead of this, we correct by the number of observations. And this is an example of the method of moments approach to estimation. And we need to set up the minimization problem because here we need to and the starting point for deriving the formulas for the ordinal least squares method for the intercept and for the slope will be to minimize the sum of the vertical distance between our observed values and between our predicted values. We've just discussed this through the figure, through the scattergram with the sample regression line. So how can we do this? The best approach, how can we minimize and how can we solve these equations? We need to use our parameters in such a manner that minimize the following equation. What can you see here? You can see here that we use the squared difference between observed values and between the estimated values. So we want to choose our parameters in such a manner that minimize this difference, this squared difference. And this is the main idea behind the least squares method. So the best way is to choose our estimators in such a way that the residuals will be as small as possible. And why ordinal least squares method is so popular? If you take a look at this equation, you can see that it's relatively easy to use this approach, or this equation, to find beta 0 and beta 1, and to solve this problem. So most other techniques involve complicated non-linear formulas or some, let's say, iterative procedures to solve the minimization problem. And also, the goal of minimizing, it's quite an appropriate form, a theoretical point of view. So, for example, minimizing absolute values sometimes are difficult mathematics. And if we minimize the square difference, it's rather easy to solve, mathematically easy to solve. And ordinal least squares estimates also have some number of useful characteristics. And when we find the answer, when we solve this equation, we can easily find beta 1 and say that these parameters are the best one. But the main rule, when we can say that the best one, if we hold all the assumptions of the ordinal least squares method. So let's again take a look, how can we do this? You can find more details how you can derive beta 0 and beta 1 from this equation. You can read Stock and Watson. I will recommend you some pages where you can find this estimation, this information about how can you derive beta 0 and beta 1. But here you can see the final formulas for beta 0 and beta 1. So again, the main idea, how can we find the ordinal least squares estimator? We need to choose the regression coefficients so that the estimated regression line will be as close as possible to our observed values, to our observed data. This is our main goal. And using some basic properties of, let's say, from this equation, we can derive that beta 0 equals this one. So a sample average of our dependent variable is an easy way to estimate a population mean. It's a natural way how can we estimate our population mean of our dependent variable. And this is how can we estimate our intercept. And beta 1, this formula give you an approach how can you estimate your slope. So this is how the ordinal least squares method estimates unknown parameters beta 1 and beta 0. And one more important idea behind this formula, that if you take a look at the numerator and denominator of this formula, you can see that here is just a sample covariance between x and y. So, and here from the denominator, you can see that this is sample variance of x. So the higher the covariance between x and y, what does it mean? That the higher the slope. And the higher the sample variance of x, what does it mean? If we talk about the denominator. Are you here?
Yes.
Okay, what does it mean if we have high value here?
Our beta 1 is less.
Beta becomes bigger.
Beta 1 becomes bigger. Yes or no?
Yeah.
Okay.
It becomes less because we divide it by sample variance.
Okay. So we discussed in details what does it mean next time, but now let's remember your answers. So also one more question. What does it mean? This sign rho. What does it mean? Do you remember?
Correlation.
Yes. So also instead of sample covariance, we can rewrite this formula in terms of correlation. And beta 1 will be just the sample correlation between x and y, and also the fraction in the sample standard deviations. Just a second, sorry. I'm sorry. Let's continue. So let's summarize the idea of ordinal least squares slope estimate. So you can see that the slope is just the sample covariance between x and y divided by the sample variance of x. You can see here this from this formula. So this is logic of this method. And if x and y are positively correlated, it means that the slope will be positive. And also we can derive if x and y are negatively correlated, it means that your slope beta 1 will be negative. And of course, we want that our x to vary will be vary in our sample. If we can see any variability in x, we will have a problem with our estimation. Please take a look at this formula to answer why. And what does it mean? It means that maybe we have some problem in our research question, or maybe we have some problems in our data set. So our data set is not very good. for our research purposes. We cannot answer our research question. And intuitively, ordinal least squares method is fitting a line through the sample points such that the sum of the squared residuals will be as small as possible. And the residuals, this one, is just the difference between the fitted line and the sample points. And that's all. And also you should remember that population regression function is something fixed but unknown, something unknown in the population. And because we never know about the real relationship in the population, we don't have such kind of data in absolutely most cases. We've just used the sample regression function instead of this. And we analyze and get our results on the sample regression function. And also we have some properties of the ordinal least squares method. And the sum of the residuals should equal 0. And this means that follows from the first order condition. You should remember from this formula that the sum of the residuals equals 0. Or in other words, we can say that estimates beta 0 and beta 1 are chosen in such a way that make our residuals sum up to 0 for any data set. And of course, some particular residuals of some observation could not be equal 0. But if we sum up all of them, they should equal 0. The second property that the sample average of the ordinal least squares residuals are 0 as well. This is obvious. And the sample covariance between the regressors and the ordinal least squares residuals is also 0. And the ordinal least squares regression line always goes through the mean of the sample. So it means that the mean value of x and the mean values of your dependent variable is always on the ordinal least squares regression line. So in other words, if you calculate and run your regression, and after you obtain your unknown parameters, you obtain them and you can plug in x mean for x instead of x, then you predict the average value of your dependent variable. And we will do this, you will practice how to do this during next seminar. And also very important terminology that you need to properly use when you run the regression analysis. So if our dependent variable is y, you can say that you run the regression of y on x in this order. Or also you can say that you regress y on x without the run. So it's very important that we regress our dependent variable on the independent variable in this order. And when you use this definition, we will always mean that we plan to estimate the intercept and we plan to estimate our slope. So when you say I regress of y on x, it means that you want to calculate, you want to obtain your unknown parameters beta 0 and beta 1. And it's very important to understand the difference between total sum of squares, explained sum of squares, and residual sum of squares. What does it mean? So if you write the y as its fitted values plus the residual, you can obtain another way how to interpret the ordinary least squares method, how to interpret the ordinary least squares regression. And we can derive from this equation the total sum of squares, as well as the exponent sum of squares and the residual sum of squares. What does it mean? So we can see that the total sum of squares measures how spread out your observed value in the sample. And if you divide this equation by the number of observations, you've just received the sample variance of y. And the same logic in the exponent sum of squares, because exponent sum of squares measures the sample variation in the estimated parameters. So in the you had, and respectively the residual sum of squares measures the sample variation in your residuals. So if you sum up explained sum of squares and residual sum of squares, you obtain the total sum of squares. One of the problem, or what can confuse you when, for example, you will read different books or different sources, you can see that the abbreviations in different sources are different, and definitions sometimes could be different. What does it mean? For example, the total sum of squares, sometimes you can see that in our case this is SST, and sometimes you can see TSS. So it could be a little confusion here. And explain sum of squares, in some books you can read that this is not explain sum of squares, but this is regression sum of squares, or instead, for example, you can see that this is model sum of squares. But all of these definitions about the same. It means, in our terms, explain sum of squares. And residual sum of squares, in some books, you can find as error sum of squares. And let's say that during our course and in the Stock and Watson, we will prefer to use these abbreviations. So we will prefer to use total sum of squares, explain sum of squares, and residual sum of squares. Even if you can find some other definitions, we will prefer this one. And also we need to talk about the goodness of fit. So after we calculate and run our regression, after we obtain some coefficients, we need to understand how well can we explain the variation in our dependent variable with our independent variables. And we can obtain the goodness of fit from this formula. So if you remember that the total sum of squares equals exponent sum of squares, or the variation in our estimated value of dependent variable, and plus variation in the residuals, we can obtain the goodness of fit. So what does it mean? We want to measure how well the explanatory or our independent variable can explain our dependent variable. And for this purpose, we need to divide our total sum of squares. And we can, after we divide this, we can divide by the total sum of squares. and say that the sum equals 1. So r squared of the regression, and sometimes we call it r squared as the coefficient of determination, defined as explain sum of squares divided by the total sum of squares. And r squared is the ratio of the explained variation compared to the total variation. And it's, let's say this is a fraction of sample variation in y that we can explain by our x variables. And according to this formula, you can assume that the results of our r squared lies always between 0 and 1, because the explained sum of squared cannot be greater than total sum of squares. So also when we will interpret r squared, we usually multiply it by 100 and interpret the result at the percentage of the sample variation in y that we explain by x. And it's obvious if all the data points, this is abstract situation. In real life, it's hardly imagined that all the points will lie on the same line. But if all the data points lie on the same line, it means that r squared equals 1. And of course, a value of r squared will be close to 0 and indicates a poor fit of the ordinary least squares line. It means that very little of the variation in the dependent variable is captured by the other factors, is captured by the x variables. And the main idea of this r squared, that of course you can use this indicator as some measure of goodness of fit. But in social sciences, in economics, in business and management, it's normal when you obtain rather low r squared in your regression equations. And not very high r squared are rather common, especially if we talk about the cross-sectional analysis, especially if we talk about the cross-sectional data. It's okay. And I want to emphasize that even low r squared doesn't necessarily mean that ordinary least squares regression equation is useless or your model is bad. Not. So even with the low r squared, it still will be possible that you obtain good estimate of your relationship between some variables. And at very beginning, students who first learning econometrics, they tend to pay too much attention to r squared. For example, they present the result of some models, they interpret the models, and they can proudly say that, you can notice that I have a really very high value of r squared, approximately equal to 0.9 or approximately equal close to 1. And because of this, my model is really very good and this is the best model. It's not true, because how well is your model, you cannot derive such conclusion from just r squared. This will be a real big mistake. So please, for now, be aware that using r squared as the main indicator of success for your econometric analysis can lead to real troubles. And you can take a look at this indicator just are the measure of goodness of fit. Plus, you need to take into account some other indicators. You need to take into account some assumptions of the model, and we will discuss what else. But for now, you need to know that this is rather popular indicator for goodness of fit measurement of your model. And that's all. Okay? So, any questions?